Today I am going to discuss synthesis, reactivity, aromatic character and importance of pyridine. To begin with, pyridine is the simplest six-membered heterocycle of azine type. So it is derived from benzene by replacement of CH group by nitrogen atom. Structure along with numbering and symbols used for pyridine has been shown here. And since we know pyridine is aromatic in nature, so from heat of combustion measurements, the aromatic stabilization energy of pyridine is found to be 21 kilocalorie per mole, which is less than benzene. So benzene is having aromatic stabilization energy of 36 kilocalorie per mole. The resonance structure of pyridine is shown here. Since nitrogen is more electronegative, so it is going to impart negative inductive effect as well as negative mesomeric effect on the ring. So it is going to carry negative charge and it is going to induce a positive charge on the ring carbon atoms. So if you come for the nomenclature of heterocyclic rings, it will be done by three ways. One is common names. So a six-membered heterocycle with nitrogen, it is commonly called pyridine. So that is one type of nomenclature. And if you come for second type, it is replacement nomenclature. Suppose if we take benzene, if I replace the CH by nitrogen, then the name given for the new compound is azabenzene after the replacement of CH by nitrogen. So that is replacement nomenclature. And third type of nomenclature is Hans-Weidmann nomenclature. Here we are going to consider the prefix ring or root word plus we are going to add suffix. So how we are going to decide the prefix? It is decided by type of heteroatom present. So in this case the heteroatom present is nitrogen. So in heterocyclic chemistry nitrogen will be called as aza. How to decide the ring or root word? It is decided by size of the ring. So as we know, pyridine it is a six-membered ring. So for six-membered, we need to use the ring or root word ion. Suffix it is decided by degree of unsaturation of ring. So if the ring is unsaturated or aromatic, and if it is 4, 5, 6 membered, then we are going to use the suffix E. So if we combine all these prefix, ring and suffix, we are going to get azine. So that is what I mentioned in the beginning, that pyridine is a six-membered heterocycle of the azine type. So this azine has been derived from the nomenclature of Hans-Weidmann. Okay, so then if you look at the basic characteristics of pyridine, so pyridine and its derivatives are weak bases with pKa value of 5.2. So why it is weak base is because it is having nitrogen which is sp2 hybridized. Since we know nitrogen is electronegative and it is having hybridization sp2, so the electronegativity will increase, so it is going to hold that lone pair of electrons, so thereby it is a less basic, or it is going to act as weak base, and whatever the lone pair of electrons, it is not involved in the aromatic sex state, so it is free, it is not involved in the resonance. So how we can enhance the basicity is by substituting electron donating group on the pyridine ring. So if we substitute electron donating group on the pyridine ring, then basicity of that pyridine will be enhanced. In which position, if we substitute electron donating group, it is going to enhance the basicity is at second and fourth position. Second or sixth and fourth position. So it is going to influence, or it is going to enhance the basicity. So there won't be any enhancement in the basicity if we substitute the electron donating group at third and fifth position. So this is some brief introduction regarding the pyridine. So what will be its aromatic character and what is its resonance energy, nomenclature and basic properties. Now the next thing is how these pyridine rings are synthesized or how we can prepare pyridine ring system. So the most well-known way of preparing the pyridine is through hands pyridine synthesis. The other approaches or other methods are condensation approach and from other ring system. So we will see one by one how we can prepare pyridine by hands pyridine synthesis, condensation approaches, and how we can get pyridine ring from other heterocyclic ring system. So first is hands pyridine synthesis. So hands pyridine synthesis it is a multi-component reaction. So where four components are going to react to give reduced pyridine. So four components, which are the four components are two equivalents of beta ketoesters, one equivalent of aldehyde and ammonia. They are going to combine at an pH of 8.5 to give reduced pyridines. This reduced pyridine, it is called dihydropyridine, upon oxidation or dehydrogenation, it is going to give corresponding pyridines. Okay, this is Hans pyridine synthesis. Hans pyridine synthesis, it is a multi-component reaction in which four components is going to combine to give a reduced pyridine. That reduced pyridine will be further undergoes oxidation or dehydrogenation to give corresponding pyridine. So this is Hans pyridine synthesis. So mechanism of Hans pyridine synthesis involves following type of reaction. First reaction is aldol condensation of aldehyde with beta keto ester. So it is a condensation reaction. So where beta keto ester is going to react with the aldehyde with loss of water molecule, it is going to form this intermediate. This is the first intermediate, that is alpha beta unsaturated beta keto ester. In simple, it is called enone. So this enone is going to react with one more beta keto ester via Michael addition reaction. This Michael addition reaction, it is an 1,4 addition reaction, or it is also called as conjugate addition reaction. So whatever the intermediate formed in the first step is going to combine with the beta keto ester to form 1,5 dicarbonyl compound. So 1, 2, 3, 4, 5. So 1,5 dicarbonyl compound will be formed. So this is the second intermediate. So this second intermediate, now it is going to combine with ammonia. So that is called addition reaction, and it is going to form imine or enamine. So whatever the imine or enamine formed in this stage will undergo cyclization reaction by the loss of water molecule to give dihydropyridine or reduced pyridine. So this reduced pyridine will undergo dehydrogenation or oxidation. Here the mechanism is given for dehydrogenation. For dehydrogenation reaction, DDQ, dichlorodicyanoquinone, is used to get corresponding pyridine derivative. So this is overall mechanism of Hans pyridine synthesis. Since Hans pyridine synthesis is a multi-component reaction, so there are several reactions will take place to give final product. So that is aldol condensation. First step is aldol condensation of aldehyde with beta keto ester, and whatever the intermediate formed in the aldol condensation step is going to react with one more beta keto ester via Michael addition reaction, and in the Michael addition reaction there will be second intermediate, that is 1,5 dicarbonyl compound. So whatever that 1,5 dicarbonyl compound is formed is going to combine with ammonia, so it is going to form imine or enamine. So that whatever the imine or enamine, it is going to lose water molecule to give dihydropyridine. So that dihydropyridine finally it is undergoing dehydrogenation or oxidation to give corresponding pyridine. So this is overall the synthesis of pyridine via multi-component reaction, that is Hans pyridine synthesis. So what is the use of the dihydropyridine? Since we need only pyridine, so there is a very important use of that intermediate, that is dihydropyridine. Is dihydropyridine intermediate prepared from aromatic aldehyde. So if we prepare dihydropyridine by using aromatic, substituted aromatic aldehyde, they are going to act as calcium blocking agents, and therefore they are valuable drugs for heart disease. So why we are using Hans pyridine synthesis and why we are getting dihydropyridine is very, why we are getting dihydropyridine is because of this reason. So whatever the dihydropyridine you are going to get, if it is from substituted aromatic aldehyde, the dihydropyridine are going to act as calcium blocking agents, and therefore they are valuable drugs for heart disease. So this is the importance of Hans pyridine synthesis. So why still Hans pyridine synthesis is used is because of this reason only, since we are going to get a very good drug molecule for the treatment of heart disease. So this is regarding the synthesis by Hans pyridine. So this is regarding the synthesis of pyridine via a multi-component reaction. So if you come for second, condensation approach to prepare pyridine. So this is somewhat simple compared to Hans. So here condensation of 1,5-diones followed by oxidation is going to give pyridine. So whatever 1,5-dione we are going to get in Hans pyridine synthesis, the same, but this 1,5-diketone we are going to get directly, and it will undergo addition reaction, and finally it is going to get oxidized to give corresponding pyridine. So for oxidation, either we can use air, HNO3, ceric ammonium nitrate, or manganese dioxide. So this is a simple approach. It is by condensation of 1,5-dione with ammonia. So if we want to avoid the oxidation step, then what we can use is, instead of using ammonia, if we use hydroxylamine, then we can avoid the oxidation step. So same 1,5-dione and reaction with hydroxylamine, so it is going to form this intermediate hydroxy dihydropyridine. So it is going to lose water molecule, so thereby we are going to avoid the oxidation step. So this is the condensation approach to prepare pyridine by 1,5-dione. So these two, the starting material is 1,5-dione combines with ammonia or hydroxylamine. So if we use ammonia, we are going to get dihydropyridine. So that dihydropyridine will undergo oxidation to give corresponding pyridine. So if we want to avoid oxidation step, then instead of using ammonia, if we replace ammonia by hydroxylamine, we can avoid that oxidation step, and in that case also we are going to get corresponding pyridine. So this is by using 1,5-dione. So we can also prepare pyridine by using 1,3-dicarbonyls and 3-amino enones. So if we combine 1,3-dicarbonyl, 1, 2, 3, 1,3-dicarbonyl with 3-amino enone, here also we are going to get corresponding pyridine. Pyridine can be prepared from other heterocyclic ring system. One such example is CMSN denstate rearrangement. What happens in this rearrangement is pyrrole on treatment with haloform in presence of strong base, it is going to yield 3-halopyridine. So these are all the methods of preparing or synthesizing pyridine. So that is Hans pyridine synthesis, condensation approach, and from other ring system. So if we come for the reactions of pyridine, pyridine undergoes reaction at nitrogen as well as at carbon. So if you carry out reaction on the pyridine, there is two possibilities. It can react at nitrogen as well as carbon. But reaction at carbon is usually difficult and slower than nitrogen. So nitrogen, it is going to react faster compared to the reaction at carbon. So pyridine is going to show electrophilic addition reaction, electrophilic substitution, as well as nucleophilic aromatic substitution reaction. So if you look at the reactions at nitrogen, due to presence of lone pair of electron on the ring nitrogen, it will undergo electrophilic addition reaction with electrophile such as protonation, nitration, alkylation, and acylation. So those will come under electrophilic addition reaction. Since pyridine reacts as base or a nucleophile and forms an pyridinium cation, in which aromatic sextate is retained and nitrogen acquires a formal positive charge. So here the pyridine can act as base as well as nucleophile, and it is going to react with the electrophile, and whatever the pyridinium cation it is going to form, it is not going to lose the aromatic character. Both are aromatic in nature, but in the pyridinium cation it is going to carry formal positive charge. So this is electrophilic addition at nitrogen. So we have to see how protonation, nitration, alkylation, and acylation will takes place at nitrogen. So protonation at nitrogen. Pyridine nitrogen forms salt with most protic acid. So if you take pyridine and if you add protic acid, it is going to form pyridinium ion. So this is an example for protonation. Whenever pyridine is added to protic acid, so pyridine is going to act like base and it is going to form pyridinium salt in the solution. So if you look at acylation at nitrogen, acid chlorides react rapidly with pyridine, generating 1-acyl pyridinium salt in the solution. So here pyridine is going to react with the acid chloride and it is going to form 1-acyl pyridinium salt. And this is a very good example which we are going to use it in the preparation of aspirin. So while preparing aspirin, we are going to use this pyridine as an catalyst. So in that one, it is going to form pyridinium salt. So that is a very good example for acylation at nitrogen. So if you come for alkylation at nitrogen, alkyl halides react readily with pyridine, giving quaternary pyridinium salt. So pyridine, if it is reacted with alkyl halide, it is going to react at the nitrogen and it is going to form pyridinium salt. And if we see nitration at nitrogen, so reaction of pyridine with nitronium salts such as nitronium tetrafluoroborates leads to nitration at nitrogen. So protic nitrating agents such as HNO3 leads to N-protonation. Already we have discussed pyridine, if it is added to protic acid, it is going to form pyridinium ion. So hence we are going to use nitronium tetrafluoroborates to do nitration at the nitrogen. So these are the some of the important reactions which will occur at nitrogen. So how we can do reactions at carbon? So electrophilic substitution of pyridine at carbon is very difficult. Two factors seems to be responsible for this unreactivity. So what are the factors? So pyridine ring is less nucleophilic than benzene ring because nitrogen atom is more electronegative than carbon atoms, and therefore it pulls the electrons away from the carbon atom inductively, so leaving a partial positive charge on the carbon atom. So in the beginning only I said this nitrogen is going to induce negative inductive effect as well as negative mesomeric effect. So thereby it is going to give, or it is going to leave a positive charge on the carbon. So if the positive charge is placed on the carbon, then it is very difficult to do electrophilic reaction at that carbon. Since already it is carrying positive charge, it is not possible to do electrophilic substitution reaction. So one more reason is when pyridine compound is exposed to acidic medium, it forms pyridinium salt. This increases resistance to electrophilic attack since the reaction will lead to doubly positive charged species. So if we are carrying out the reaction in acidic medium, then it is going to form pyridinium salt. So if it is going to form pyridinium salt, then it is going to have double positive charge. So obviously it is going to resist the electrophilic attacks. So these are the two important factor which will make the electrophilic substitution reaction at carbon very difficult. Hence pyridine is bad at electrophilic aromatic substitution reaction, but under drastic condition pyridine ring reacts with electrophile only at third position. So why it is going to react at third position? So this is the reason why in the third position it is going to react. So if it is going to react at second alpha or gamma at fourth position, then in the intermediate the positive charge will reside on the electronegative atom with sextate configuration, which is not favored. Okay, so in both alpha and gamma position the positive charge will be placed on the nitrogen. Already that nitrogen is sextate, so it cannot bear that positive charge. So these two are unfavored reaction intermediates. So such case is not possible in the case of beta substitution. Hence it is going to react at third position, but it is slower than that of benzene. So this is the reason under drastic condition why it is undergoing electrophilic aromatic substitution at carbon. So alpha and gamma position in the intermediate stage, the nitrogen is going to carry the positive charge, and since the nitrogen is in sextate state, so it is electron deficient, so it cannot be favored to place the positive charge on the nitrogen. So but in the beta such case is not possible, so hence at drastic condition we can do electrophilic aromatic substitution at carbon. So these are the examples for electrophilic aromatic substitution reaction at carbon. So if you want to do nitration on the carbon, so we need to maintain 300 degree centigrade. We need to use concentrated H2SO4 and concentrated HNO3, but initial stage it is going to form pyridinium cation, but since we are maintaining higher drastic temperature, so it is going to give this 3-nitropyridine, but the yield is mentioned it is around only 6% is formed. And if you want to do sulfonation of pyridine, so if we do sulfonation with H2SO4 sulfur trioxide, we are going to get low yield. But if we use mercuric sulfate along with the sulfuric acid at 220 degrees centigrade, it is going to form this quaternary salt of pyridine. Then it is going to rearrange and it is going to give the sulfonation product, and the yield is around 70%. And if you come for nucleophilic substitution, it is very easy with pyridine. Electrophilic aromatic substitution reaction is very difficult, whereas nucleophilic substitution reaction is very easy with pyridine. And which position is more reactive towards the nucleophile is 2 and 4. Why? Because if the nucleophile attacks at second or sixth carbon, so it is going to have an resonance structure where the negative charge will be placed on the nitrogen. Here nitrogen is going to act like electron, since hence it is favored. So this resonance structure is possible only in alpha and gamma, means second and fourth position. So if we see at beta position, that is third position, there won't be such resonance structure is possible, so hence it is not favored. So nitrogen atom makes pyridine more reactive towards nucleophilic substitution, particularly at second and fourth position. So because of these two resonance structures, so nucleophilic substitution reaction will take place only at second and third. So if we see the example for nucleophilic aromatic substitution reaction, so nucleophilic substituents favored by electron withdrawing substituents that are also good leaving group. So a nucleophile will be easily get substituted if the electron withdrawing substituents are present, and at the same time they are going to act as a good leaving group. So if the pyridine is having electron withdrawing substituent, then nucleophile can attack and it will be substituted when that new electron withdrawing substituent is also a good leaving group. The position of leaving group influences the rate. So where that leaving group is present, that is also matters in the case of pyridine. So if it is in fourth position, it is the relative rate of leaving is more compared to second position, and it is least in the case of third. Okay, so this is relative rate of leaving group. So this is very important. If a reaction is given and we need to decide the relative rate by the position. So gamma position, if the leaving group is present at gamma positions, so its relative rate will be more compared to alpha, and it is very least in the beta. So that is in the case of nucleophilic aromatic substitution reaction. Substitution reaction also occurs through formation of pyridine intermediate in pyridine, so which is similar to benzene, and they are very reactive and they cannot be isolated. So whenever pyridine having halogen, if it is treated with sodium amide, it is going to form intermediate pyridine, so which is similar to benzene intermediate, and it is going to show the nucleophilic substitution reaction. And here also pyridine will be formed from both gamma and beta. So whatever the product it is going to form, the gamma product will be in higher yield and beta product will be in lesser yield. So this is very important. Anyhow, both are going to form pyridine, but which will be the major product is the gamma product. Gamma substituted product will be major product and beta substituted product will be minor product. That is, we have already discussed. So nucleophilic substitution reaction will be favored only at second and fourth position. Here the nucleophile is going to add at beta, here the nucleophile is going to add at gamma. Next is metal halogen exchange reactions. Pyridines can undergo metal halogen exchange reaction when treated with butyl lithium. So if we have halogen substituted pyridine, if we do the reaction with n-butyl lithium, then it is going to form lithium derivative. So this lithium derivative, it is going to behave like aryl lithiums or Grignard reagent and reacts with electrophiles such as aldehydes and ketones and nitriles. So if we see the reaction of lithium derivative of pyridine with ketone. So whenever we are going to take 3-bromo pyridine, so when it is reacted with butyl lithium, it is going to form a lithium derivative. So if this lithium derivative is treated with ketone or reacted with ketone, it is going to form the product which is similar to Grignard reaction or organolithium reaction. So it is if we are taken ketone, so it is going to form a tertiary alcohol. The same lithium derivative of pyridine, if it undergoes reaction with nitrile, so this is the reaction. So it is going to add to the nitrile and it is going to form iminium salt. So that it is going to take proton and it is going to form imine intermediate. This imine intermediate will undergo hydrolysis to give corresponding ketone. So this is reaction of lithium derivative with nitrile. So where this lithium derivative is going to act as nucleophile. Is deprotonation of alkyl pyridines. Deprotonation of alkyl pyridine occurs in presence of strong base, and deprotonation occurs only with alkyl groups at alpha and gamma position, not with beta position. So why the deprotonation occurs at alpha and gamma substituted alkyl pyridines is because the reason is resonance stabilization. So whatever the anion it is going to form by deprotonation or abstraction of hydrogen, so it is resonance stabilized. So this is in the case of alpha alkyl substituted pyridine, and this is in the case of gamma substituted alkyl pyridine. So there will be resonance stabilization, and whatever the hydrogens attached to that alkyl group, they are acidic, so they can be easily get abstracted, and after abstraction there will be resonance stabilization. So hence alkyl pyridines with alkyl group at alpha and gamma position, they show deprotonation reaction. What is the use of this deprotonation reaction is the whatever the deprotonated intermediate, it is going to react further, it is going to react with electrophiles like aldehyde, it is going to form alcohol. If it is reacted with carbon dioxide, it is going to form corresponding acid, and if it is reacted with alkyl halides or alkyl bromide, it is going to form corresponding alkyl derivatives. So that is the use of the deprotonation reaction. If the pyridine ring is attached to alkene, then conjugate addition occurs. Suppose instead of alkyl group, if there is an alkene or if there is presence of double bond, so then instead of undergoing deprotonation followed by reaction with electrophile, what it is going to do is it is going to show conjugate addition reaction. So this is how it is going to react with the nucleophile if there is presence of alkene or if the presence of double bond. So this double bond is in conjugation, so this double bond will shift and this nitrogen is going to take the negative charge and there will be formation of positive charge here. So since there is creation of electrophilic center here, so nucleophile is going to attack at this carbon and it is going to show the nucleophilic substitution. So this is the difference. So if there is alkyl group, there is abstraction of proton and it is going to react with the electrophile. So if there is any double bond, then it is going to react with the nucleophile and you are going to get corresponding substituted product. Next, the important reaction of pyridine is Chichibabin reaction. Here pyridine undergoes nucleophilic reaction with hydrides and the reaction with lithium or sodium amide is referred to as Chichibabin reaction. So pyridine will undergo nucleophilic addition reaction with hydrides. So and it is going to form 2 amino pyridine, and that is called Chichibabin reaction. So this is also one of the nucleophilic addition reaction, and it is going to take place at alpha position. So here is the example for bioactive pyridines, nicotine and isoniazide. Nicotine is a pharmacologically active constituent of tobacco, but it is toxic and additive. So whereas isoniazide contains an pyridine heterocycle, so it is used an important agent used to treat tuberculosis. Okay, so and several drugs will have pyridine nucleus. So hence the study of pyridine heterocycle is very important. And I will stop at this stage. Thank you.